Okay, good evening, dear students. In last class, we discussed about the Carnot cycle. In that Carnot cycle, there are four steps involved. One is isothermal expansion. Next, that is second one is adiabatic expansion. That is isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression. And this is studied in yesterday class completely, and today class I am going to discuss about the this Carnot cycle net total work done. Here the total net work done by the gas on completion of the cycle. You know, I already written in last class the complete process, that is W, the work done is W is equals to WAB, WBC, WCD and plus WDE. Here the unit name is thermodynamics. Here therefore W is equals to WAB plus WBC, BC plus WCD plus WD or AEW area in process, that is W is equals to WAB plus WBC minus WCD minus WD. Write the obtained equation 1, 2, 3 and 4 here. In WAB is RT2 log of V2 by V1. Therefore, this is equals to R T2 log of V2 by log of V2 divided by V1 and plus here WBC, that is CV T2 minus T1. You will get a T1 minus T2 and you get a positive T2 minus T1. CV into T2 minus T1 minus WCD. WCD is the RT1 log of V4 by RT1 log of V4 by V3. Here V2 by V1 and another V plus CV T1 minus this minus WDA, you get that is plus of CV into, I write directly, minus CV into T2 minus T1 minus CV T2 minus T1, and this is a positive CV T2 minus T1 and this is a negative CV T2 minus T1. Here this is this one positive and negative, and you get the RT2 log of V2 by V1 minus RT1 log of V4 by V3. This is equation number 5. Equation number, you know, up to here in first process equation number 1, in second process equation number 2, and in third process equation number 3, in fourth process equation number 4, and this is equation number 5. Therefore, this W is equals to R T2 log of V2 by V1, V2 by V1 minus R V1 log of V4 by V. This is equation number 5. This is equation number 5. You get equation number 5, and the net heat absorbed by the system. Therefore, the net heat absorbed by the system, then the net heat absorbed by the system or gas or gas in the whole process, that is what whole cycle, in the whole cycle or a process, in the whole cycle. And here we get that you write Q is equals to heat is absorbed, that is Q is equals to QAB minus QCD. QAB minus QCD. You get CD and AB. This is AB and this is a CD. QAB minus QCD. Therefore, the equation is you add Q is equals to QAB means RT2 log of V2 by V1 minus RT1 log of V4 by V3. This is equation number 6. Q is equals to R. This W is equals to Q. You know formula. Q is equals to RT2 log of V2 by V1 minus RT1 log of V4 by V3. This is equation number 6. And here, therefore, by considering or by comparing this, you are considering equation 5 or comparing equation this 5 and this equation number 6, it can be concluded that the essential addition for the cyclic processes is to be satisfied or completely satisfaction is that this is equals to W is equals to completion is that is or complete satisfaction of this corner cycle process is equals to you get a W is equals to Q, how much heat is absorbed and that work is done in this process in a corner cycle. The corner cycle is very important, that 6 marks question, corner cycle process. Here W is equals to Q, or in other words the work done is maximum, hence the heat absorbed by the gas is equal to the work done here. The heat is absorbed here, that is the work is done maximum. The work done is maximum, hence the heat absorbed by the gas is equal to the work done by it, and which is agreement with the first law of thermodynamics. This is agreement with the first law of thermodynamics. Up to here, you write in your examination for 6 months question. Next, entropy. Entropy, you know, it is a randomness or a disorder. Here, according to the concept of entropy, what is meant here? The entropy is denoted as here in the thermodynamics S. The change in entropy is delta S. This is a change in entropy, and here the entropy is denoted as S. Here, the entropy is a measure of randomness or disorderness of the system. Here, the entropy is a measure of randomness. Entropy is a measure of randomness or disorderness. Entropy is a measure of randomness or disorderness of the system. And the numerical definition of this entropy, the numerical definition of entropy according to Clausius. He told the Clausius, according to numerical here, the Clausius is told, according to Clausius, the definition of entropy is the entropy of a system is constant quantity and there is no communication of heat flowing out of the system. He told this definition according to Clausius, scientist here, and of a system and produces corresponding decrease in the entropy. When heat flow into a system of the entropy increases by the factor Q and T, Q by T. Thus the entropy can be defined as here according to Clausius for a reversible change taking place at a fixed temperature T and the change in entropy delta S is equal to the heat energy absorbed or evolved is divided by the temperature. This is known as the entropy. Here the entropy is defined as for a reversible change, for a reversible change, for a reversible change, reversible change taking place at a fixed temperature, reversible change taking place at a fixed temperature at fixed temperature T at fixed temperature T and changing entropy and changing entropy delta S, changing entropy delta S is equals to the heat energy absorbed. The heat is equals to the heat energy absorbed, heat energy absorbed or evolved divided by the temperature, divided by the temperature. Here, this is a definition of entropy and according to Clausius, here the entropy is a measure of randomness or disorderness of the system. You write this one, and here according to Clausius, here for a reversible change taking place at a fixed temperature, the temperature is fixed and the reaction is reversible change, fixed temperature and change in entropy delta S. The change in entropy. S is a entropy, delta S is a change in entropy. This is equals to the energy absorbed, which is equals to the, that is here the heat energy. The heat energy is absorbed, the heat energy absorbed or evolved divided by the temperature T, the temperature T, and that is the change in entropy. You can write that is delta S. Delta S is equals to heat is absorbed divided by temperature is T. This is equation number 1. This is equation number 1. Here you get equation number 1, that is change in entropy. This is a change in entropy. Heat is absorbed Q and temperature is fixed T. This is equation number 1. If heat is absorbed, then delta S, that is heat is absorbed, and here this delta S, that is a change in entropy, will be positive. Here you get the change in entropy will be positive. and there will be increase in the entropy. Here the heat is absorbed, then delta S will be positive and there will be increase in the entropy. Here this heat is absorbed, entropy is increase here and it get a positive value and increase in the entropy. And if heat is absorbed means it get a positive value and it is absorbed. Then heat is evolved, then delta S is get a negative value, there will be decrease in the entropy. Here heat is absorbed, heat is absorbed, absorbed, it is absorbed. Here you get a positive value and entropy increases. Entropy increases. And here in case of heat is evolved and it get a negative value and entropy decreases. Here the entropy decreases. This is decreases, this is increases. And here the unit of this entropy is joule per mole per Kelvin. The unit of entropy is joule per mole per Kelvin. This is the unit of entropy. This is one question. Define entropy and another write the unit of entropy. This is a joule per mole per Kelvin. Here the variation of entropy for the factors depending upon the two variables. Here the variation of entropy. Here you are varying the entropy for the factors depending upon the two variables. One is a temperature and volume. Two variables. One is temperature and volume. Temperature and volume. And second is a two factors. Second is a pressure and temperature. Pressure and temperature. These two are depends on the entropy. When you are entropy's variation takes place, they depend on the two factors. One is the temperature and volume, and another is the pressure and temperature. We will discuss first one, the entropy change by temperature and volume, and afterwards the entropy change, the pressure and temperature. First factor, entropy change by the entropy change by the temperature and volume as variables. Temperature and volume, temperature and volumes as variables. In two factors depending on the entropies changes or variables. Here the entropy change by temperature and volume as a variable. Volume as a volume. Volume as a variable. Here, let us consider in this. Let us consider n moles of an ideal gas. Here, let us consider n moles of an ideal gas. N moles of an ideal gas. N moles of an ideal gas. And ideal gas and occupying volume V. Here occupying volume is V. Volume. Here occupying volume is V. And at pressure and temperature. And pressure is P. Here pressure and T temperature. Here you consider, let us consider the volume n moles of an ideal gas occupying the volume V at pressure P, temperature T. If the system absorbs heat reversible, then increase in entropy. Here the system absorbs heat, therefore here the system absorbs absorbs heat reversibly. The system absorbs heat reversibly. Then increasing entropy. Then increasing entropy. Then increasing entropy is on the equation here. The increase in entropy is ds, that is here increase in entropy ds is equals to q divided by dq, difference dq divided by t. dq divided by t, this is a reversible. The reaction is reversible. This is equation number 1. Right here reversible. Okay, we have it, and here you get the equation is ds is equals to dq divided by dt. It is reversible, and this get a equation number 1. Then according to the first law of thermodynamics, okay, right here the continuation reaction equations. Here the first equation is dq is ds is equals to dq divided by t. This is equation number 1. After, according to the first law of thermodynamics, according to first law of thermodynamics. First law of thermodynamics, you know, according to first law of thermodynamics is, that is reversible. dq is equals to the work done, that is dE plus P into D. This is according to first law thermodynamic. First law, dq is equals to heat is observed and here energy, and it is a pressure. Here dE plus P into D, and here you write this and this one, and finally get ds. You have dq value in this here. This dq value is dE. dq means dE P dV, and here dE plus P dV divided by T. You get a equation. This is a equation number Right? Equation number 2. Next, you know that is the ds. You write this, simplify this one. ds is equals to dE divided by t plus t into dV divided by t. d, you write separated these two, t by t, p dv by dv. And this is equation number 3. This is equation number 3. Okay. Next here, dE by t plus p dV by t. Here, you know the formulas. PV is equals to nRT. PV is equals to nRT. You substitute P value here. P is equals to nRT by V. nRT by V. Okay, here ds is equals to dE by t plus p dV divided by t. Here PV is equals to, consider PV is equals to nRT. Here P is equals to nRT by V. Next here the CV is equals to dE by d. CV is equals to dE by d. CV into dt. Therefore dE is equals to CV into dt. You substitute these values in this equation. That is CV is equals to dE by dt. dE is equals to CV into dt. And PV is equals to nRT. P is equals to nRT by V. You get the equation is where here the CV is the molar heat at constant value, where here where CV is the molar heat at constant volume. CV is the molar heat at constant volume. And substitute the equation. You consider equation A and B. You consider this is the equation number A, and this consider the equation number B. Substitute equations A and B in equation 3. Here, this is the equation number A and this is equation number B, and these two values substitute in equation number 3 in this equation. And here we get that is ds is equals to here dE divided by dt. dE means here CV into dt. dE means CV into dt. CV into dt divided by dt. And here plus nRT. This here nRT divided by V. P plus P in place of P replace nRT by by V. nRT by V into dV by dV by T. dV divided by T. Okay, see here ds is equals to, this one is a CV into dt. Okay, CV into dt divided by t, and here you get ds, that is a d is equals to So here you write another n CV, that is a n moles. You are taken here n moles. You write this is a n CV. N CV, and this is also you take here n CV. And see here n CV into dt divided by t plus n RT divided by v into d, and you get finally that is a NCV. This is t and this is dt, and here v dv t and t. Only you get n, or you write here v into dv, or you can write this one here NCV plus nr dv divided by plus nr divided by you can write here the nr and NCV. Here ds is equals to, in the another form, NCV, or here you cancel here nr plus nr, here NCV nr, and ds is equals to, take n is the outside, NCV plus r. See, this is a CV plus r, and here you add the s is equals to, you get ds is equals to NCV dt divided by t. Here NCV dt divided by t, therefore plus nr, this nr divided by t, or you write t is cancelled here, nr divided by v into t. This is, you get the equation, and next you integrate this equation ds NCV dt divided by t plus nr dv divided by v, and we integrate the equation between limits. Here you add limit s1, ds is the s1 and s1 to s2, and here t1 to t2, this t1 to t2, and this v1 to v2, and integrate this equation. Here the integration of ds s1 and s2, the limit is s1 to s2, and second one is NCV dt divided by t is t1 to t2. Here therefore this is equals to the integration of limit t1 to t2, here NCV dt divided by t plus integration of this one v1 to v2, limits is v1 to v2, only nr v into t. The limit is v1 v2, here nr v into t. Okay, you integrate this equation, that is a ds, the limit is s1 to s2, and here the dt t1 to t2 temperature, and here volume v1 to v2, and you get the s. This is a, you apply the limits ds, here you get a s, in place of s you replace limits s2 minus s1, upper limit minus lower limit, here s2 minus s1, therefore is equals to, you take out NCV is the constant outside, that is the dt by t is the integrate, that is you get a log of t1 to t2, and nr to take outside, and you integrate dv by v, and you get a log of v1 to v2. Here therefore s2 minus s1, this is equals to the t1 to t2 is a limit, this is constant you take outside, NCV into log of integrated this one dt by t to log of, here log is t here. you get T1 to T2 plus here n of log of V, here V1 to V2. You apply degree means lower limit and upper limit and lower limit. Then you get in place S2 minus S1 NCV log of T2 minus T1 V2 minus V1. You write the delta S is equals to 2.303 into bracket NCV log of, finally you take here you take a log 2.303 log of this one. I am here. Therefore this is, you write delta S, change in entropy here is S2 minus S1, delta S is equals to delta S D, here ds, that is you write D delta S. Delta S is equals to NCV log of T2 minus T1 plus N or log of V2 minus V1. Therefore, delta S is equals to 2.303 NCV T2 minus T1. You write the T2 minus T1 is the T2 by T1 and V2 minus V1 is the V2 by V1. That is equation number. Here you get equation number 2, equation number 3, you get equation number 4 here. Here NCV log of T2. This one you write log of, when it is subtracted to division, when it is division you subtract log of T2 by T1 plus N or log of V2 by V1. This is equation number 4. This is equation number 3. That is equation number 4. And finally, you get that is a 2.303 NCV log of T2 by T1 plus N or log of V2 by V1. This is equation, that is equation number 4. Here the entropy change by temperature, volume, variables. Only it changes temperature and volume variables. Therefore, delta S change in entropy. Delta S is denoted as change in entropy. Therefore, 2.313 NCV log T2 by T1 plus N naught log V2 by V1. This is a formula. You get this formula for changing entropy for variables are temperature and volume. Okay, I will stop here. In next class, I derive this entropy change by temperature volume is completed. In next class, the entropy change for the temperature and pressure as variables. Here, temperature and pressure as a variable.